Okay, folks, how are we feeling about this complex analysis? You start reading it?
Not yet.
Okay, and we have homework 7 ready?
Yeah.
Okay. So for today, we're going to talk a little bit about the relationship between the real and complex part of any imaginary, or I should say a complex variable z. So we talked about them in the context of u and v. You remember that? Okay, so what's u?
It was the real or the imaginary part?
Oh yeah, use the real part.
Okay, so here's the trick. Which one comes first in the alphabet?
A, B, C, D, E.
You have to do it that way? Which one's first, U or V?
U.
U is, very good. So which one's real?
So U.
Okay, so let's just write a few things down. U, a real one, there you go. That's a great mnemonic to remember it. Don't say welcome to me, I don't care. All right, ready?
Yep.
So the first thing that we're gonna say is we're gonna say Z is equal to, now Z of course is a function, X, Y. What do we write that as?
X.
Okay, that's one way to write it for sure.
Or U.
That's a way to write it. Is that the only way to write it?
No, you can also do
Of X, Y.
U versus Y.
U of X, Y.
Plus I B image.
Correct. Now, why is this second way more general?
There might actually be like.
There could be X and Y that's real and X, Y that's not real.
Sure. But isn't that here?
But then there's only Y on the imaginary.
Ah, exactly. So we do say that when we think of like a complex number, you think of it in terms of the real plus an imaginary part. But in reality, when I say something like a complex variable, that's different than a complex number. So for example, Z might be a complex number where I might say something like 4 plus I times 3, right? Or 3I, right? That would be an example of a complex number. Whereas Z generally is a complex variable. And as we saw in the earlier discussion, we showed 3 different examples of complex variables where U, for example, was a function of X or Y or both, and similarly with V, right? So let's go back to that idea. Let's ask one more question. Here is a function of a complex variable, f of z. Okay. I'm going to write this as x squared minus y squared plus I 2xy. Is that okay? What's u? Good. All right, let me write this down. Function of a complex variable. Okay, and what's the v?
Yeah.
2xy, right? Good. So now the important question. Can I use the Cauchy-Riemann relationships to find out whether this is differentiable? What are they?
dv dy or partial equals partial u partial x.
Sorry, dv dy equals?
Du dx.
Good. And?
Negative dv dx.
Okay.
Equals du dy. Well, yeah.
Is that okay? Did I just switch those? Okay. Okay, so let's use them. Get the brain working. What are
Negative 2y is negative 2y, 2x equals 2x.
they? Okay, good. So walk me through this. So this part here,
That's
dy,
2y.
this is
2x.
d, right? 2x, okay. And this one?
2x.
Right, so this piece disappears, and this becomes 2x. And that is equal. Good. First relationship. Second one.
That's dx, so that's 2y. And then that is also 2y.
Why not? So this one here.
Yeah,
Negative
it's
negative.
derivative of negative y squared.
All right, so is this differential?
Yes, it is.
Good, and have we seen it before?
Yeah, that's it.
Yeah, the first one we saw, right? Or the first one that we found that was differential. Okay, good. So this is how we use the Cauchy-Riemann relations. They have some more properties that we're going to investigate today. So let's ask a different question. Here's the function, let's write it here. These are absolute value symbols. Okay, what about that one right there? Is this an analytic function? In which domains of the complex string? What's this? Welcome, Dr. Grandma. Get out of here. All right, so let's remember that the complex plane R. This. Okay, you have four regions. I need 1, region 2, 3, 4. That's it.
Okay, you can't write 1, 2, 3, 4. I did it Roman.
Is that right? Yeah.
Yeah, that's right.
Okay. All right. So in which of these locations is which of these domains is this function analytic?
Isn't it just 1 and 2?
How are you guessing?
Well, it's the absolute values of x and y.
Sure. But how are you guessing that? Are you using any information that we've talked about today?
Well, I haven't done any calculation.
Let's start with that, right? That might be the place to start. What's you?
X, or absolute value.
This one? Right? And with y? Oh, sorry, with z?
Is it? Yeah, it's the absolute value.
Is it?
Negative absolute.
Negative absolute value of y. This piece matters too. Okay. So let's ask the first question. What's dx?
0.
Good. And is it 0 everywhere?
Yeah.
Okay. And what about d minus du dy?
Also 0.
Good. Ditto. All right. So that's great. That's the first part. Now let's ask the second part. dv dy.
I forgot, when you take the derivative of the absolute value, would it just be 1 or would it be?
Like, are you asking if it gets something different?
Yeah, like would there be some sort of condition that goes with it or is it just 1?
Well, we want to think about each of the 4 domains. Right? So the easiest thing to do, for example, is to imagine in the first quadrant where x is x is greater than 0 and y is greater than 0. What do we get there?
That would be -1.
Correct. And that's all you have to say, right? You can just say 1 in
1.
yes, 1 in 1, -1 in 1, right? And similarly, how would we describe this for this one? For DUDX.
1 and 1.
It's 1 in 1, right?
It doesn't even.
Good. Okay, so is this analytic in region 1?
No.
Right? Okay, let's do the next region.
Same.
Is it?
The Y is not. Well, even if one of them's negative, it'll just become positive. Right?
Even if one of them is negative, it'll just become positive. Is that what you're saying? So for x less than 0, the derivative here is -1.
Well, what about the absolute value?
Right, so think about what that means in the absolute value when you're heading in du dx. Which direction, what does the absolute value look like?
It's like.
Here, it goes like what?
It's like a.
Good. And that slope is?
1.
1. Good, what does it look like in that quadrant?
It's also here.
You see?
Um,
Right, it's this. So is it analytic in quadrant 2?
yeah.
Bada bing, bada boom. Okay. Does that make sense? That one maybe is not so obvious, but when you see it written and you see the slope, that gives us the indication of what's going on. Okay. What about in the bottom?
So like, let's look at region 3. So region 3, that'd be negative. Could be actually 1 in region 3.
UX. 1 in region 3, yes.
And then PBY.
Oh, 3.
She didn't say that again?
I don't know why I forgot that was 4, that was 3. I was trying to do the left, that was 3.
Oh, yeah, sorry, I'm going from here to here.
It's 5.
Yeah, so dBby, so it can be the derivative of negative absolute value of y. Y is negative in region 3. So then that's just -1 in region 3.
So
it's a
what is equals 1? I don't know how the slope would look though.
Yeah, that's a good question.
Do you draw it or no?
Can I draw it in the, well, so for this one here, this is the let's look at this piece here. This is dv dy. This is minus the absolute value. Right? So what is that? Minus the absolute value? Flipped over, right?
They're all just eggs.
Well, this one here, let's look at this one. Okay, this is dx. Yeah, that one's fine too. Okay. Maybe not a fun picture or a pretty picture. What's another thing we're noticing here? This is analytic in certain locations. So we said that it's not analytic here. It is here. It's not here. And it is here. Okay. Let's talk a little bit more about the relationship between some of the Cauchy-Riemann requirements and also the implications that this has on how we interpret things like, we heard of the word the modulus of Z, from the argument of Z.
Is that like modulo?
Not quite. So modulo would be how many are left over. Modulus is like the magnitude more or less of a vector. But in this particular circumstance, when we talk about complex numbers, we say there is a modulus and an argument. Okay, you might also say this about something that is like um, like a sine or a cosine. You would say like the amplitude and the argument of the sine or cosine. Okay, so we're gonna try and understand these numbers a little bit more, and then we're going to build a power series of complex numbers. Can they be represented by something like a Taylor series? And then we'll ask the important question: how do functions work? Right? So, for example, can I take the exponential of a complex number?
There's Euler's.
Sure, there's Euler's. A different way of asking this is that we still want to think about whether or not these things are analytic. So is the complex exponential analytic? And that may not be immediately obvious to you. Another question is the natural logarithm, or maybe the logarithm as a whole of a complex number, is that analytic? And what I mean by that in particular is, if I take the logarithm of a number, do I get one value? Or do I get lots of values, right? Because that's going to be really important to understand. Okay. So let's write a few things here. Have you heard of the complex conjugate?
Yeah.
Okay, so you're familiar with the complex conjugate. So you could write something like this. X is equal to 1/2 z plus z star, where z star is the complex conjugate. Is that true?
Yeah.
Do you know what this means?
Yes.
No. What is the complex conjugate?
So the complex conjugate is you, assuming that you have like the definition of z based off of that, the complex conjugate of z would be x minus I.
Ah, okay. So let's look at this. Let's see if that works.
Is that a Z in the front or a 2?
Oh, this here is a 2. I'm always going to draw lines through in order to clarify that, because when I would do my own homework, I would find that I wouldn't be able to tell the fucking difference. Okay, so here if I add the complex conjugate to the value itself, the reason that we have the complex conjugate at all is so that we can get rid of this imaginary component. So by definition, this is how I would write x. How would I write y? Is there a clever way to do that? Probably good.
So writing I as its complex conjugate, or is it
Probably solve for X. Plug in.
Probably solve for x and plug in. Well, let's have a look at these two forms.
Oh,
x minus z?
1 over 2. I like that. Why do I like that? Because it's going to get rid of the fact that I have two versions when I do the adding. And I'm also going to have an I by definition when I add the two components. And then what do I have? Z minus Z star. Cool. Okay. So technically, this is fun. If you think about x and y as a combination of a complex number and the complex conjugate, then I can represent add, oops, u plus iv. Well, that could really be a function not of x and y, but of z star. Right? Right or wrong? This is a different way of writing this information. Right? These are definitions. We don't have to argue about them. And that leads to this realization about the Z star. Now we'll have to do one more thing. We'll have to say something like, well, what is del F del Z star?
What is like the definition of the derivative, like with the limit is equal to 0? Or?
No, we don't have to do that here. We have a relationship already between the x's and the y's and whatnot. I just want to know if you were to change variables like this, if we define z star, how do I turn this into something that I've seen before? For example, I want to understand this differential. The first thing that I need to write no, f can be general here, and we can think about it still in a generalized context. First thing that I'm going to do here is I'm going to write the chain. Right?
That's smart.
This is the relationship between our new variable, z star, and the old one that we're familiar with. We're going to see if we can get anything interesting out of this understanding. Am I done? Why not?
Why?
Because you need y, of course. So now I add that, d add dy and
dy over t.
very good. All right, so now we have some interesting parts. Do you know what f is? F's up here, right?
We'll have to do command T.
Excuse me?
We'll have to do the dx for u and v, right?
We'll do the dx for u and v. First of all, what's this one here?
That be 1/2.
Right. Folks see that? And what's this one here?
1/2i.
Good.
Or negative.
Yeah. Okay. And of course, what happens when I pull the I up? If I put the I not on the bottom, but on the top. Good. So I can set this equal to
I over 2.
again. I like I's on the top, just easier for me to look at. Okay, good. So now let's rewrite. What? Okay. So let's take f. We know what f is, and let's apply the derivative. So what's this piece here?
That'd be cu dx
Correct.
plus I dv dx.
Good. That looks like a 2, it's not. Okay, and then this one here is what? You what? I can only hold so many letters in my brain at a time. Okay. That's interesting. Huh. Really, really, really fascinating stuff, right? What's the sequel to? Go ahead and add all the imaginary and non-imaginary parts in the same locations, right? Group them. All right. What do we got?
1/2. See. Yes. Minus. PBY.
Okay. Plus I was parentheses, BB over U. Plus BU over U.
That's interesting. What does that tell us?
Good, so that's like the real imaginary parts of the project.
Sure, but does that look like anything I've seen before?
This is capture remark.
You tell me. Are they?
And if the Cauchy Riemann is true, then that would be 0.
Right. So let's think about the implications of that for a second. Now, what is it that we calculated? We calculated the derivative of f with respect to the complex conjugate. And the Cauchy-Riemann relations seem to indicate to us here that if f is a function of a complex variable, z, then it must be arranged such that the complex conjugate is not present. We can't have functions of the complex conjugate if the Cauchy-Riemann relations are satisfied. So if the function is differentiable, it's analytic, then therefore it is not a function of the complex conjugate. Does that make sense? Okay. Kind of weird, right?
I noticed that you labeled it wrong.
What did I say? Oh my God. Thank you.
Whatever.
Yeah, that's probably.
You get it. You get it.
It's complex.
Complex. It is a complex number and conj. Okay.
Wait, so going back to this.
Yeah.
All right. If the Cauchy-Riemann, equations are correct, then this should equal 0.
Not should equal 0. It does equal 0.
Will equal.
Right? So what is the implication? So this implies if f of z is analytic, then z is only found as x plus I1. Not is that okay? That's the implication, right?
Trying to get this exact phrasing for this. So this implies that if the function is analytic, then the function is only of C, not of Z conjugate.
Yes, exactly right. That's exactly the way to think about it, right? So if you see a function with Z conjugate in it, you already know that it's not analytic. Is that another way to say that?
With respect to the complex conjugate of 0.
Okay. So let's do one final thing when talking about the Cauchy-Riemann relations, and then we can talk about our functions. So, you know, we have fun in this class, and we just like to take derivatives of fucking random shit, right? Y'all love derivatives? Okay. So let me ask you a question. What happens if I take my Cauchy-Riemann relations, let's take this one here, and let's take a derivative with respect to x. So this is our CR1, and this is CR2. Oops. And let's take ddx of the left-hand side of CR1. What's that? So that's going to be ddx of.
Sorry, I zoned out for a second.
Okay, let's read that again. Let's take a partial derivative with respect to x, of the left-hand side of the Cauchy-Riemann relation 1? So the left-hand side is what? Du dx, right? Left-hand side. Okay, so let's do du dx. And that's going to be equal to the right-hand side, which will also have a d dx, but now of dv d1. Right, that's fine, right? You okay with that? And we can flip the order of derivatives, or is that?
Yeah, we can.
So let's imagine what happens when we take, say, flip these out. Go d dy dv dx, right? But what is dv dx? Negative du dy. How do you know that magic trick? That's CR2. dv dx is negative du dy. So let's write that up there. So that's minus e dy du dy. That's interesting. What did I just do there? So on the left-hand side, way over here, I have two derivatives with respect to x. Here I have two derivatives with respect to y, and it's the same function, right? So what did that top part say? Just take the beginning and the end and set them equal to each other. Move one over.
That's where you.
If you put the x derivative of the first relationship, the y derivative of the second relationship, is it equal to each other?
So interestingly enough, these first two lines, push your head like that. So this first part here is the x derivative just of the left-hand side. And then this is the x derivative of the right-hand side.
But you did x for the first one and y for the second.
No. They're both x. So x and x, right?
Yeah.
But when I got to here, I realized I could swap these.
Oh, so it's the same thing, but you swapped them.
So I just swapped them. But then I looked inside and I said, well, this thing really
Second.
is this other one. Right?
Yeah.
And so now I have two y derivatives because I swapped one out and I got one from CR2. And so I have this one here with two y's and this one here with two x's. And I'm just going to put them on the same side. They're applied to the same variable u. And now I have a relationship between the Laplacian.
What about the negative side?
Well, it was on the other side, remember? Other side of the equality.
Oh, you added.
Yeah, so
Sorry, I got lost.
Yeah, no worries. It's a weird line, right? So the first two is the original equality. This line from here to here is the swap. And then this line from here to here is recognizing that that's the right-hand side of CR2, right? And then this line moves it over so that we can see what it's equal to. Okay. Now, you tell me what happens if I take ddx of dvdx.
Take dx dx.
Yeah. Using this logic.
Take the second relationship.
Yeah, so do the same thing I did here. Start here on the left-hand side. Take a derivative with respect to x. And see where you get. You get the same thing?
So,
Well, that's a different thing, isn't it?
Well,
We got to be careful with our words here because we get the same thing, then I'm worried. We get a similar thing, then I'm fine. So what'd you get?
Yeah.
Okay. I'm trusting that you all did this on your own. Is that unusual? What have I written? Fucking nose, bro. Yeah.
sorry, I'm actually not sure how we actually got that.
All right, Reed. Now's your time to shine.
So we have the partial x, and then we try to see the partial to be a partial x.
Yeah.
And then that's equal to because of dx is dx or negative dy.
Okay.
And then we do the same thing with the swap. It's swap to the dy. And it shows them the du dx is now d.
That's using this one. Left hand side of CR1, right?
Yes, that has to be.
So you do the same thing twice. You use the relationships backwards, right? Okay. And you get these two statements. What is this thing called again? The d squareds. Remember the term of that?
Oh,
Laplace.
Laplacian. Yeah.
Laplacian. Laplace is the guy. Laplacian is the operator.
Oh, okay. And that's a gradient square.
Not the gradient square. The gradient, of course, gives you it's del squared, right?
Right.
And that's not, I mean, that's not on you to memorize, but
Yeah.
remember that every time that we have one of those triangles, if it's a bold triangle, then that takes a vector, or sorry, a scalar turns it into a vector by into, you know, rank 1 tensor. Here, this thing, right, is going to give you, and we'll show that in a little while. You could do del of u, and you could get the gradient. That would be the directionality in each slope. We'll talk about the curvature, but what this is separately saying is that the Laplacian of u, the Laplacian of v are both 0. Okay? So this separately solves Laplace's equation. Into v. Okay, so there's constraints on what u can be and what v can be in order for the function to be. Okay. Cool. Okay, I'm not going to go, I mean, we'll use the curvature and we'll use gradients a little bit more when we talk about this in the functions of a complex variable. Let's talk really briefly about power series of a complex variable. When's the last time you all saw power series? What?
Been a while.
Been a while.
No, I've ever seen them in class.
You've never seen them in a class?
What is that?
You didn't see them in math method 1? I'm not shocked that you haven't seen them. I'm shocked that that wasn't presented to you by
Well,
whoever.
maybe it was, I think.
Now, power series is not me-like,
Yeah.
right? It's like
Yeah, like 1 over.
Sure. Yeah, that's close. Yeah. Typically, you know, that'd be 1, might be some other variables. So we're gonna generalize it a little bit. Let's leave that up there. What?
No, that's forget.
I forget everything. That's why there's notes in my book. There's not notes in my book, you're not getting a lecture. Okay. So in general, we could say something like this. Let's say f of x, now this is a normal power series, right? What do I rate that? I don't know.
Oh, the power series.
Well, the naming seems like it's gonna be a series of powers that get bigger.
Good. So let's use all that information. Series means
Adding,
good. That means
summation.
sum. Good. And you said it's a series of powers of
X.
very good. Okay, so let's write all that out. That looks good. Are we done?
No, there might be some coefficient on the screen, like.
Very good. And how would I write those?
I think it's a something.
Very good. There we go. And now what are we gonna do here?
Oh,
N equals 0
And to infinity.
to infinity. To infinity. All right. We did that. We're good.
yes.
Okay, everyone's seen that. Okay, so now let's ask the question, what about z? Oh, you like the same thing? I don't know why it would be different. That's perfectly fine. So let's write the same thing. N equals 0, infinity, a of n, z of n. Right? Z is a complex variable here. Is a real?
I want to say yes.
Is the imaginary is Z?
Okay, that could be true.
Wait, a gets multiplied by z at each sum.
A gets multiplied with z at each sum.
So there's a real and an imaginary component in that a case of it.
They'll have to be, right?
Okay.
Because otherwise this thing, which is complex, necessarily will have multiplication types of this. It's pretty complex. So this is definitely a complex variable. That's not an obvious to anyone. But this is generally there, of course, are examples where it's not. Does that make sense? So how do I write z in terms of its modulus and its argument?
I don't know those words mean.
I don't even know what that fucking means, bro. Okay. Now I'm always allowed to write z like this. Legal or not legal? Sure, what did I say? So let's look back at our domain. Here's x, here's iy. Let's find some point z. Okay, so z can be the x and iy components. That's perfectly fine. You might even do a little drop down. There's your x. Here's your iy. Good. And then this vector, so to speak, not really a vector, but you know what I'm saying. It's z. Okay, so now what do I define here? If I want to think of it in terms of the modulus and the argument.
What's your modulus and argument?
Good. This is the argument. Theta. The angle from x. This length is the modulus, r.
You can't do that with x and iy, it has to be theta and r.
What do you mean x and iy?
You said modulus was like the magnitude?
Yeah, what's the it's the definition of the length of r.
So
So for example, you might say something like this, right? R equals the combination of
x,
length.
so if you want to do modulus in x and y, you have to make it X. You have to turn into a length.
Well, the modulus just means the length.
Yeah.
Right? Whereas the argument tells you in which angle, which quadrant it lives. It's basically a conversion between Cartesian coordinates in a complex plane and polar coordinates in the same complex plane. Is that okay? Well, we just call it modulus and argument. Is that fair? So let's rewrite this. Okay, the sum doesn't change. AN doesn't change. What do we get next?
Probably R to the N.
Very good.
Then E that I and theta.
Okay, I'm gonna write the exponential, and you'll see why in a little bit. I n theta. Very good. Okay. Does this series converge? Don't ask me questions I hate.
Over E to the I gets bigger. So
Yeah, what does e to the I look like? And then remember that you're saying e to the I, but I'm pushing us against that. I'm saying it's an exponential of I and theta. So we talked a little bit about this at the beginning. We said it was a whose relationship can we use to turn this into something more meaningful? Not Cauchy readings. He's got his name on everything. It's got a U and some E's. Euler relationship. What does the Euler relationship teach us about e to the I theta?
Oh, it's cosine.
Is it just cosine?
Cosine.
What?
Oh,
How?
Cosine plus I.
Plus I sine.
Yeah.
Okay, so when I think of a complex exponential, really what I'm thinking about is the fact that, and I kind of drew it here without even acknowledging it, e to the I theta is a more compact way to describe rotation around the complex plane. Sine theta plus I sine theta give you the contribution of those with respect to the real and imaginary components. So what are the values that a circle can have? Radius 1, good, right? So you can't get outside of that radius 1. So we can ignore the e to the I n theta in terms of convergence, right? So what do I have to know in order to know if this series converges? Yeah, because it's not really an exponential. Remember that it's not an exponential if there's an I in it. You see exponential with an I in it, you think sine and cosine. And you just told me that the magnitude of that can never exceed 1, right? So that is not contributing to this discussion of whether or not this thing is diverging or converging.
oh, is it like the R of N?
I don't know why I thought the R of N could only be 1 then, so that's why I was confused.
Ah, so the radius is what tells us how far away we are.
Yeah.
Right? The circle is on the unit. The circle's on the unit circle. C'est bon? Okay, so let's look at this argument then. Let's say this thing here must do what? Has to converge. If this doesn't converge, then this doesn't converge. Right? So to express something as a power series, we should have it converge, right? Because that would be a little silly, right? You take some sum up to infinity and you get the answer infinity. Right? Not useful in terms of mathematics. So in order for this thing to converge, this thing has to converge, right? So we can in fact make a definition, and this is a fun thing to do. You can test this, that there is a radius of convergence R, specifically 1 over R, such that the limit as n goes to infinity. Ooh, that's a bad idea. Of a to the n. Ooh, that's better. 1 over n. Okay. So this is convergent. Absolutely, if Z is less than R. And outside of it, divergence. Whew. That's a lot of words, Guzmani. I ain't reading all that, right? So let me ask you a couple questions here. Let's use some of this, right? Okay, we have a Z-plane. We have some series. Let's write a couple of series down. I'm gonna write one series for each of you because there's 3 of you. Fucking genius. Okay, let's write the first series, which is, I'm not gonna write the, all right, here's n equals 0, infinity. You want the easy one. How do you know which one's the easy one? Excuse me? What?
For the last series, that's n.
Yes,
Okay.
all of them are n. C's and n's only. Okay, pick one, agree upon it, and tell me what the radius of convergence is in the real plane. Reed, jump in first. Early bird gets worms.
Okay,
I'll get the second one.
I'll take the third.
Let's go, boys and girls.
Ask one question? Yeah. Does that mean that a to the n equals whatever is multiplied by z to the n?
Does that mean a to the n equals whatever is multiplied by z to the n? Yeah, by definition, right?
Yeah, so the first one would be 1 over n factorial equals a to the n.
Right. No, don't do that.
I have a.
Don't use your brain, please, for 1/2 of 1 second. This should not take more.
My paper and I did it and I wanted to make sure I have the right paper.
Calculator. You ever seen me use a calculator my whole life? That's true. Okay, got me. You got me. What did you have?
I had the second one.
Okay, so what is the second?
I think the radius is 1.
Why do you think that?
Because, okay, so you have to take the limit and then put it to infinity of n factorial. At the value of n factorial to the power of 1 over n.
Okay.
So I interpreted n factorial as just like infinity. So infinity to the power of 1 over infinity, that's just infinity to the power of 0, that's 1.
That's not true.
Yeah, that's right.
No, hold on. Not all infinities are infinity. Right? So there's a power of different infinities. N factorial is not n. Infinity factorial is not infinity. It's much larger than infinity. Because it's infinity times infinity minus 1 times infinity minus 2, right?
Yeah.
Okay, so let's think about that a little bit more closely. What is the limit of n factorial as n goes to infinity? Yeah, better be.
Yeah.
Right? And the 1 over n, basically, you can ignore the shit out of that. This thing's going off to infinity and it doesn't even care. So what's the radius of convergence? Okay, let's try that again. Here's the first question. The limit as n goes to infinity of n factorial 1 over n is infinity. Solidly so, right? Okay, so let's look at your question here. What's your radius of convergence?
Because you keep taking bigger, like.
Yeah, let's think about 1 over, right? What does this thing mean?
So it'd be 1 over 2.
The nth root or something, right? Okay. The infinitieth root of infinity factorial is?
I guess you have to multiply infinity times itself.
Right, infinite number of times. So therefore, at minimum, you'd get something that was infinitely large. Right? And this is maybe a little math dumbness to discuss, but at minimum, this is a pretty big infinity. Good. Now what? What does that tell you about your radius of convergence?
Yeah, now it's 1 over r is equal to infinity.
Okay, so what is r?
0.
It has to be 0, right? If I switch the two locations, I put 1 over infinity, I get 0. Identical. So this thing, and if you look at it, maybe it makes a little bit of sense. It doesn't converge anywhere except for
0.
at z equals 0. It has to only converge at z equals 0, right? Because look at the fucking first term, it's a factorial. And the factorial goes to infinity, right? Okay, all right. So we already got that one was fine. So this one, the radius of convergence is
You apply the same logic like that.
no, but reverse logic. That sounds math. So what do you mean by that? This one here?
That would go to 0.
Yeah, 1 over r.
1 over
Whatever n factorial.
whatever n factorial definitely goes to 0.
Yeah.
Which equals 1 over.
Which equals 1 over r.
Yeah, so then the limit of 1 over to that one is going to be.
Ah. So where is yours valid?
Everywhere.
Very good. So that's how we say it, right?
Same for me.
Okay. Why would I do that? Why would I give 2 of the same answer? That doesn't seem realistic. There's no trick involved in yours? All right, so let's think about yours for a moment here. This is n.
Is n not big enough? For the n factorial?
Well, let's have a look, right? So we have something like the limit as n goes to infinity of what's that? 1 over n.
1 over. What would you multiply by itself 1,000,000 times to get 1 over n?
What? I don't understand that. So as n goes to infinity, let's think about the opposite of that. Let's imagine n to the power of 1 over n. As n goes to infinity, what's the lower limit that you could have?
So if that was just n in there, as you go to infinity,
You get
So n to the power of 1 over n, is that what we're talking about?
yeah.
And then it's infinity to the power of 1 over infinity, which is 0.
the infinity root, right?
Yeah.
Not 0.
So
The lower limit would be 1. And the limit of this, actually, you can show is 1.
Also, then the radius of conversion.
Yeah. Weird, right? So this is absolutely convergent only if z have you seen that before?
Yeah, I remember doing this.
In fact, this radius of convergence argument we made in power series discussions. Because if, for example, you have a z that's, or an x, when we're thinking about real numbers, if it was larger than 1, it would diverge because of the powers of n. If it was less than 1, it was fine. You'd get an answer, right? Okay. Fun? All right. Let's talk about our exponential. We could beat this thing to death, but you've seen power series now. You've seen how to use some complex numbers in the radius thereof. So let's I'm going to delete this now. So we said this exponential. What's that mean? What?
Isn't that like when you like try to phrase exponentially, that just e to the power of whatever?
Sure, but let's pretend that we're mathematicians. So we'll be a little pedantic here. What do we mean by e to the power x? Is there a way to write, say, a power series to describe that? Now that we know that we can write power series, we're going to build every step, right? We're going to find out whether exponentials are, in fact, whether they're in.
would it be the same thing, just instead of x stand, it's e to the n?
Well, you can't use e in order to describe e,
Yeah.
right? We want to define what e is. Exponential, that the function itself is unknown to us, right? Let's imagine that we're, 1700s mathematicians.
I was just thought it was a random number they picked for natural laws.
So the exponential, for example, that's based in the natural letter e.
Yeah.
But it doesn't have to be, right?
Base 10.
You can do base 10, or you can do other bases.
I don't know
Right.
why they picked like 2.7.
Well,
Maybe.
what do you mean they found? What do you mean they found? They weren't walking around the forest and they found E and picked it off a tree. Like, it is true that it shows up over and over in the natural sciences.
Yeah.
Right, and there is absolutely this curve that has this beautiful function where E is represented this way in a binary number system. Oh, sorry, in a decimal number system, right? So you use a base 10, E is this natural curve. But if you use something like the Aztec's base 60, that's not necessarily the case, right? Okay, so natural is a misnomer. We still created it based on our choices. But more importantly, how do we define the exponential? So the exponential of z is a power series. And in fact, you've seen this power series. Hope you have. N equals 0 to infinity. What's the top part? C to the n. Good. What's the bottom part? And factorial.
Yourself, good job.
What? What?
I thought it was funny that we were answering and you told yourself, good job.
I didn't say that.
Good job.
I may have said, you heard good job? Definitely did not say good job. I'm trying to figure out what I didn't say though. I just sounded like that. Fuck, I have to watch the tape back. It's good that it's recorded. So the top part of it here, the C is going to the power n, and on the bottom it's the n factorial. Where have I seen this before? Oh shit, right here. Whoa, that's the exponential. And what did we just find out about it?
It's everywhere.
It converges everywhere. So good. So we have a power series representation of this thing that converges everywhere. Now the important question is,
Why?
is it analytic? Okay. So let's look here. He said z to the n, n factorial. It converges in absolute radius everywhere. Yeah, we're good here. Okay. So this has to be analytic over the whole z plane, right? Because it converges absolutely over R, right? Might have time for this. Do you want to do an example, or do you want to see some funky stuff? Okay, so let's ask the question. Let's define A to Z. So how do I write that in terms of our exponential?
It's conversely.
We don't know about that power series. We didn't. I mean, I didn't show you that in another power series like that conversions.
C. E.
So let's assume A is a real number. That's the first thing. Let's assume A is real and greater than 0. Okay. So I would define the complex exponential, which is A to the power Z, as the exponential of and the natural log of A.
Oh.
Good. Okay, so now we get to have a little fun, right? ln A is the natural log of A. In this particular case, A can equal E, if we want that. And then you can have the natural log of E be 1, and that would write the exponential of Z would of course be the exponential of Z. Oh, good. Whew. That's a fucking equality, right? So now we're seeing, okay, so we can switch between these two very easily. So Z is real, then we get the old definition back. That's really important. I always want to check that. What about for Z equals IY? Let's write this down. Let's write what's the exponential Z? That is the exponential of IY, which is
That oh, that's a.
Let's use the summation.
no. Let's use the Euler.
Oh yeah, it's Euler, then it's sine.
You like using only one half of it. I've noticed. We always want to use both.
Oh, because I put in, oh, okay, yeah, but I thought I put in like the I, so I thought the cosine would cancel, okay. No, it's in the parentheses as well. Oh, I get it.
Okay. So that's the z part. That's interesting. So what's the exponential of z when we think about it in the context of the exponential of x? Well, we could add in, of course, the extension for that z equals x plus iy. What would that mean? Just separate them. You get e to the exponential of x, right? Times that. That would be okay, right? I'm asking whether or not we can write this. How would we write e, exponential of z, where z is written in this way? I'm giving you examples of how we're using these functions. Okay, so now we begin to think about, well, what the fuck are we doing here? Okay, so as z varies over the complex, we're running out of time. It's always happens. We should have a 2-hour class. Do you guys want that next semester? I guess you'll be gone. You'll finish. For I don't know, for all my classes.
Oh,
Okay. So we'll just clarify really quickly here at the end. Z varies over the complex plane. So the modulus of x x e to the z takes all real values. Right? Here's the modulus. Do you see the real part here? Good. Except that is 0. However, the exponential of z can vary, right, based on the argument of y. Is that true?
it's imaginary.
Why? I'm agreeing with you. Why?
Yeah.
Right?
Yeah.
Not WHY, but why?
Yeah.
When you think about this in terms of the modulus, right? How big is the thing? And the argument of the function, theta. What are we ending up with here? Are we ending up with a single value function?
You're saying if you change y, does that affect whether or not you get multiple values?
Mhm.
Maybe, yeah, because you can make one, like either sine or cosine 0, the other one 1.
Sure, but let's imagine now for a moment that you add to any y 2 pi, then what do you get?
Same thing you get.
Aha, an issue, right? So in fact, this is now multi-value.
You can't get the same number and a different y.
What do you mean?
Like normally on a graph, you can like go up, you can like go back to a number, or no, you can't. Never mind.
Okay, yeah, that's
I
fine.
forgot.
Yeah, we're working through that in this version, right? So you could definitely do it this way. You could get 2, right, y's. You shouldn't get 2 x's. And so in the same way, we shouldn't have a dependent variable giving us 2's. Okay, we're going to look at the implications for this, for things like sine, cosine, tangent, hyperbolic tangent, etc. But this is the major difference between the functions that we're used to and the ones that we're about to see, where now we have to worry about the argument and the modulus, right? Because they will give us distinctly different answers. Oh, sorry, same answers for distinctly different functions. Questions? Okay. It's that time of the year. You should tell me how much I suck. Go into Canvas and write a 10-page report. Fire this motherfucker right away. No tenure. Okay?
Okay.
No, don't say that. Please don't say that.